Welcome everybody to this afternoon's panel session, Next Gen Thermal Management Applications. We have three fascinating speakers and me. So I'll be moderating. I'm a little bit of the odd duck out, so I'll do a quick introduction and then invite Alexander, Prahit, and Brett up so that they can give an introduction, and then we'll get into some panel discussions and then leave enough time for question and answers from the audience as well. So I guess I should say a little bit about my background, which I failed to do this morning. I spent 44 years now in aerospace and energy engineering systems. A lot of it has had thermal management as kind of the through thread in all of it. But the other piece of it that has been consistent is liquid hydrogen cryogenic systems. First with my work at NASA, where I spent most of my career, and then with other customers. So I was going to talk just briefly in my introduction comments about liquid hydrogen and thermal management of liquid hydrogen systems and the synergies that are possible with various mobility platforms that you're beginning to see some design concepts are starting to do, but a lot more could make use of it. So let me just start very quickly with an introduction to hydrogen storage options. So hydrogen can be an energy carrier, an energy storage media, or a fuel. And it can be used in a fuel cell or in a combustion process. And all of those are in play right now and have been actually in some industries for a long time, but more recently in emerging industry sectors. You can store it underground in salt caverns. There's several of those already in place and many more capital investments in that category. These are generally for things like grid energy storage, long-term kind of seasonal storage where you can put a lot of hydrogen into these large salt caverns. The next one, which is a lot more common, has been around a lot longer, is some people call it solid-state storage, material-based. It's essentially either adsorption or absorption into a matrix material of some type, where metal hydrides are the most common. So you have to generally provide some energy to get it back out, usually heat. The other methods are a lot more common, particularly as you start moving to mobility platforms rather than stationary systems. Those include compressed gas, and now commercially available up to 700 bar is quite common, 10,000 psi. The other one, which is more what I'm going to talk about in terms of thermal management, is cryogenic liquid. That's been used for 60 years continuously in the space industry, very large scale, cradle to grave, whole life cycle, production, storage, loading onto the vehicle, and then usage, of course. But it's a very specific use case, and now you're starting to see it moving into these other applications where not changes, but paradigm shifts have to be made to make use of it. The last category I won't talk a lot about. It's more emerging in the commercial sense, although it's been under investigation and research for several years, is cryocompressed. Depending on your point of view, it has either both the best or the worst of both worlds of compressed gaseous hydrogen and cryogenic liquid hydrogen. You've got to keep it cold, but you can also get fairly high densities, and it's all in a single supercritical phase, so you don't have to worry about liquid, vapor, and sloshing and that sort of thing. So just a quick overview there of the different hydrogen storage methods. This is now getting more into the thermal design options. So this is my own taxonomy. Other folks use theirs in the cryogenic world, but I like to think of it in terms of, and this is usually the order I tackle it in system designs. First of all, passive methods. So this is mostly material choices, trying to get thin conduction lines into your piping, any sensors if you're using them, structural members, that sort of thing. And then moving down into insulation choices. Liquid hydrogen is almost always, for most applications, in a vacuum jacketed dewar. Similar to a thermos, you basically have a vacuum space between two walls. The inner wall holds the liquid. The outer wall is subjected to the environmental temperatures and environment in general. And then in between, you have a very hard vacuum and generally some insulation. And there's various types, multi-layer insulation being the most common to get the very high performance. And then you can move in at the other end into active. You can have refrigeration and cryo coolers. You can actually maintain liquid hydrogen without any vaporization whatsoever if you have a cryo refrigeration system in place. And we did put that capability into the largest liquid hydrogen dewar at Kennedy Space Center. It's 5,000 cubic meters. the largest operating one. There's much larger ones, actually, double that size or more, that are under design and going to be demonstrated in the shipping industry soon, within the next year or two. And then somewhere in the middle are some other ones, other hybrid methods where you're using the Joule-Thomson cooling effect with hydrogen once you get below a certain temperature, or you're destratifying the liquid to bring down pressure. There's a lot of those types of techniques. So it's a bit of a world of its own when you get into cryogenic thermal management. It's different than ambient temperature and even different than high temperature applications. But what I'd like to talk about, I think that's more maybe germane to this conference, is what are the synergies that are possible when you've got a cryogenic fluid like liquid hydrogen as your fuel, and now you're putting it onto a mobile platform. So here's some quick examples. Waste heat from superconductors. So since you have liquid hydrogen, which the only cryogenic fluid that's colder than liquid hydrogen is liquid helium. So hydrogen's about 20 degrees Kelvin roughly. That gives you a lot of cooling capacity to have superconducting motors, superconducting wires potentially. The motors in particular, there's a good deal of work that's been going on for many years in that arena, and now there's actually applications of the capability to integrate it into these mobile platforms. Airframe structure heat, so if you've got heat coming in either from aerodynamic heating, if you're talking about aviation or other aerospace applications, but it also could be other structural heat for different applications. And then finally, fuel cell rejection heat, or it could be combustion engine rejection heat, essentially ways to package the system such that you can reduce the amount of heat exchangers you've got to heat exchange with, let's say, ambient temperatures, which are a lot. You can get a lot colder cold sink with your liquid hydrogen. And then, of course, the through line through all this is you need to vaporize and then warm that hydrogen up for most propulsion systems and fuel cells anyway. So adding this, getting the synergy of dumping these weight heat loads into that liquid hydrogen stream actually benefits two things. You're vaporizing it, you're getting it ready for the fuel cell or an engine of some type, and you're cooling down key subsystems. I think I have one more slide here. This is an example in the aviation arena. So again, you've got two aspects of that thermal management. How do you keep the liquid in the state you need it in? So that's a lot of cryogenic engineering. And then how do you warm it up? How do you pressurize it? Again, these are all synergistic ways that you can use the liquid hydrogen. And then what power plant are you feeding it to? And of course, the output is, if you're talking about fuel cells, water vapor, essentially. If you're talking about engines, combustion engines, you get water vapor and some NOx production. The one thing about hydrogen is you can run at very low, very lean mixtures that aren't possible with other fuels. So you can actually lower that NOx much lower than you can with other fuels. And NOx production is essentially, it's a high temperature process. So any combustion process, you're going to produce NOx. It's a dissociation of air and then recombining into NOx. So that's a quick introduction into my area. This is just a quick QR code for those that might be looking into this or interested. I have a lot of resources and tools available, interactive tools online and so forth.